Hi, I'm Natalie, the Heme Queen, and my home is here at Medetto Studios, where medical education meets 3D meets very interesting stories. I'm a board-certified hematopathologist, and I'm also a 3D CGI artist. Here is the blood flow of my first ever YouTube video. I'll talk about the history of the blue people of Kentucky, methemoglobinemia, the oxygen dissociation curve, and much more. If you like my content, don't forget to subscribe, like, and comment. The story begins in 1820 when a French man named Martin Fugit married Elizabeth Smith in Hazard, Kentucky, a town near Troublesome Creek. They had 7 children together, and 4 of them were born with blue skin. Now fast forward to the 1960s to the University of Kentucky. Doctors were talking about the blue people of Troublesome Creek, how they lived these long lives to their 90s with good health, but no one knew why they were blue. Some of the comments I got when I posted the mini version of this video on TikTok were, I have to get out my phone, "I would love to see how it looked on them," meaning the blue skin. And another person wrote, "Okay, for the non-scientific of us, how blue is blue? A bluish tinge, duck egg, sky, or royal blue?" So I don't think I can post a picture here of the blue people, but I've matched the blue color of their skin to a rendering I made of an arm so you can understand how blue we are talking. Now back to the story. Dr. Madison K. Wine, a blood doctor, got really curious after hearing about these blue people, wondering if perhaps their blue skin had something to do with his favorite subject, and also my favorite subject, blood. So he jumped in his car and drove 8 hours from Lexington to Hazard. He met a nurse named Ruth there at a heart clinic, and it turns out she was also very curious about the blue people and wanted to help them. And so for a while, the two of them started looking for blue people. They would spot a blue person, and then it really sounds like they chased after them, but the blue people always got away. Finally, a blue husband and wife walked into Ruth's clinic. Dr. K. Wine was thrilled. They were incredibly embarrassed by their blue skin. He examined them, he checked their hearts, normal. In fact, everything was normal except for their blue skin. He asked if the blue couple had any relatives with blue skin. They both said yes. He traced their blue skin ancestry all the way back to Martin and Elizabeth from 1820. He also drew their blood. And instead of being bright red like normal blood in a test tube, it was brown. He ran all sorts of tests on their brown blood, but everything came back normal. He was stumped. One day he came across an article talking about people with blue skin in Alaska, which sounded a lot like the blue people in Kentucky. The author thought they had a disease called methemoglobinemia and theorized that this was due to something missing in their blood. Let me explain this a little bit. So our blood has a lot of red blood cells in it. About 25 trillion red blood cells are in our body right now, floating around in our blood. And inside a single red blood cell, there is a lot of hemoglobin within it. Hundreds of millions of molecules of hemoglobin in a single red blood cell. Hemoglobin is made up of 4 globins, and each globin has a porphyrin ring, and in the center of the ring is an iron molecule here in silver. Together, the ring and the iron make up heme. It's the iron that picks up oxygen from the air we breathe in our lungs, carries that oxygen, and delivers it to everywhere else in the body. Iron reversibly binds to oxygen, and 4 irons means 4 possible oxygens per hemoglobin. But there is a catch, a chemistry catch. That iron must be in a 2 positive or 2+ state to bind oxygen. This 2+ iron is also known as ferrous iron. I've rendered this 2+ iron with a silvery look. If you removed an electron, a negative thing from the iron, you would change the iron to become more positive. It now changes from 2+ to 3+, and this 3+ iron is now called ferric iron. I've rendered it out to be green now. The chemistry word for taking away an electron is oxidation, so the ferrous iron was oxidized to the ferric iron. And something that did the removing of the electron is called an oxidant. Now, this green 3+ iron is a huge problem because it can't bind oxygen. So you might be wondering, what about the other 2+ irons? Can't they continue picking up, carrying, and delivering oxygen? Not quite, because this 3+ iron causes even more mischief for the entire hemoglobin molecule. That 3+ iron changes the remaining 2+ irons to grab oxygen even more tightly and not let it go. I think about it like adding a green magnet onto the 2+ ions. So the 2+ ions can grab oxygen, but they can't let it go, and that means they can't deliver oxygen. So this entire changed hemoglobin with this 3+ green iron and these super grabby green magnetic 2+ ions is called methemoglobin. We can see this change a bit better with the oxygen dissociation curve. So when I was in medical school, this graph gave me total nightmares, but now I think of it a bit differently and a little bit less textbooky. So the oxygen dissociation curve is plotting how hemoglobin and oxygen play together in the body. Let's set it up. We'll start with the x-axis. So on the x-axis is how much oxygen there is in the environment of the hemoglobin. And we're measuring that oxygen in partial pressure from 0 to 100 millimeters of mercury. And that is a tongue twister. From here on out, I'm just gonna say oxygen levels. And our chemistry pals and experts, feel free to chime in and comment. So oxygen is a gas, and as a gas, it exerts pressure. If you were to collect gas in a container, the force of a gas pushing against the container is the pressure. The air we breathe is a mixture of gases. It's mostly made up of nitrogen, 78% here in orange. 21% of air is oxygen in blue, and the rest is small amounts of other gases, including carbon dioxide with less than 1% in it. The total pressure of this mixture of air is atmospheric pressure, which is 760. If we only want to talk about oxygen alone in this atmospheric mix, we can refer to its partial pressure, which I think of as oxygen's individual pressure role in the mix. So since the air is 21% oxygen, 21% of 760 is 160, which is the partial pressure of oxygen in the air. When we take a deep breath into our lungs, we inhale this oxygen level of 160 into our alveolar spaces. And now our air mixture changes in the alveolar spaces. The recipe changes a bit in the amounts of gases and what is in it now. So when we inhaled that air into our lungs, water vapor got added and carbon dioxide increased. Nitrogen and oxygen also decreased. So now oxygen takes up about 13%, which comes out to about a level of 100. So on this x-axis, I've plotted 0 on the left here, represented by the red planet Mars, since there's hardly any oxygen there, and on the right is our lung at 100. And the whole goal of hemoglobin is to take this 100 that is in these alveolar spaces and deliver it to the rest of the body where the oxygen is lower. On the y-axis is our hemoglobin saturation. Saturation means the percent of hemoglobin that is bound by oxygen. It is also a number 0 to 100, but it is a percent. And I like to make this super simple for myself. I think about it as a single hemoglobin molecule on the y-axis that kind of speaks for the rest. So here's that single hemoglobin on the left, and it's split up based on how many oxygens have bound to it. I think about saturation in quarters since we have 4 spots for oxygen to bind to. So if we go from 0 to 25%, that would mean 1 oxygen has bound to 1 iron. If we go from 25% to 50%, hemoglobin is now half occupied with 2 oxygens, and so on. So let's just leave the oxygens up here on our y-axis. Now, this 50% saturation is super important in the curve because the partial pressure of oxygen at which 50% of hemoglobin is saturated is called the P50. And this value will haunt us. I'm just kidding. This value gives us a lot of information without needing to plot or see this entire graph, and there'll be more on it in a little bit. So before we plot methemoglobin on here, let's do the normal first. Now, I like things simple, so first let's plot what we know. Let's start on the left at 0 oxygen. So with no oxygen around, there's nothing for hemoglobin to bind to, so the saturation would be 0. So we can put a dot at 0 and 0. So now let's go to an oxygen level of 100. If there is a lot of oxygen around, it's very likely it will bind to hemoglobin and saturation will be high. So let's put a pink dot at 100% saturation for an oxygen level of 100. So we've got our 2 points, and we can create our curve in 2 ways since the binding is reversible. Hemoglobin both binds to and lets go of oxygen. Starting at the top, so as fully saturated hemoglobin travels to lower oxygen areas away from the lung, it's generous. It will normally want to give up oxygen. At a level of 27, it will release 2 oxygens and now be 50% saturated. 2 spots are taken, 2 spots are empty. And then around 20-ish, it will release its last one. And then when we've hit 0 oxygen, we have 0 saturation. Now, another way to think about this, the binding of oxygen on the way back, ready to load up. So at 0 oxygen, there's no oxygen to bind, so saturation is 0. Eventually, when you hit an oxygen level of 20, you can find an oxygen bound to hemoglobin. To get that first oxygen onto hemoglobin, it took us an oxygen level of about 20, and it was a bit tough to do. However, after that first oxygen binds to hemoglobin, something called cooperative binding happens, and then the next 3 oxygens kind of pop on more easily. So that first oxygen increases the affinity of the heme molecules to grab even more oxygen. So instead of waiting for another 20 millimeters of mercury of oxygen to get our next oxygen on, it only takes about 7 for the second one to pop on, which is now our P50. And this is that one value you really need to know in the curve, the P50. It's 27 millimeters of mercury normally. After hemoglobin is 50% saturated at a level of 27, a third one pops in at roughly an oxygen level about 40-ish, and now you can see that this curve is getting S-shaped or sigmoidal because after you get that first one in, the rest are easier to put on hemoglobin. And then that curve will plateau with higher oxygen levels since the available binding sites on hemoglobin are already occupied by oxygen. Let's look at methemoglobin now. On the x-axis, the 0 to 100% is the same, but to illustrate this change, I've added some magnets to it. So we'll start at the bottom. So we know that methemoglobin is going to grab oxygen quickly and hold on to it tightly because it's different from hemoglobin now. That ferric 3+ green iron has now increased the affinity of the remaining 2+ irons. Remember those green magnets, and so now we have an increased affinity for oxygen. So those remaining grabby green magnetized irons are going to bind to oxygen at lower oxygen levels. They are thirsty, they are greedy, so they're going to get 50% saturated at a lower oxygen level than 27, just because it's so grabby and has a higher affinity. So we can put our P50 at about a level of 20, knowing that that P50 is lower than that of normal hemoglobin. So even if you don't have this graph, just knowing this lower P50 value means higher affinity, like a higher attraction to oxygen. So now let's take the reverse. Let's talk about methemoglobin letting oxygen go. It doesn't want to let it go. Even at the normal P50 of 27, it looks like it might not even give up any oxygens. So the whole curve has shifted to the left, and that's why it's called left shifted. And the P50 also shifted left. So if the P50 is lower, it means it has a higher affinity for oxygen. Magnetic indeed. Here are some other things that shift the curve left. Fetal hemoglobin, low 2,3 BPG levels, hypothermia, since colder weather stabilizes the bond between iron and oxygen. Hemoglobin won't want to give up oxygen so easily. We all have a teeny bit of methemoglobin in our blood, but it's no more than 1%. And this low level is maintained by an enzyme called Cytochrome B5 reductase found in our red blood cells. I've rendered it out to look like a blueberry for us, and I'll explain why in a bit. We have thousands of enzymes in our body, and I like to think of enzymes that are things in our body with assigned jobs. Cytochrome B5 reductase is an enzyme that, using its blueberry hand here, adds back an electron to that pesky 3+ green iron. It reduces, like its name reductase, that iron from a 3+ to a 2+ state. I made it as a blueberry since I always remember hearing that blueberries are full of antioxidants. Antioxidants are reducers or adder backers of electrons, so the opposite of oxidants that remove electrons. So after the hand of cytochrome B5 reductase throws a purple electron back in, that reduced silver iron can happily go back to binding oxygen, and methemoglobin changes back to normal hemoglobin. This enzyme keeps our methemoglobin levels in check. High levels of methemoglobin is called methemoglobinemia. Back to Dr. K-Wine and our story. He reads that article and wondered if the blue people of Kentucky also had methemoglobinemia that was caused by missing this cytochrome B5 reductase. He immediately drives back to Hazard and finds that blue couple. and they introduce him to their blue aunt and uncle. Dr. K-Wine draws all of their brown blood and rushes back to the hospital. He runs a test to check if there's cytochrome B5 reductase in their blood. And here is our setup. Normal blood on the left, 4 brown tubes on the right, and we are looking for the blueberries. He ran a more sophisticated test than this. And the test results were none of the brown blood samples had the enzyme. So all his blue patients were truly missing this enzyme, and it caused their methemoglobinemia. They had methemoglobin levels of about 10 to 20%. So Dr. K-Wine wants to help get rid of their blueness. If they're missing this reductase, they need a replacement of sorts, another reducer or an antioxidant to donate an electron to reduce the 3+ iron back to the 2+ iron. And no, it's not blueberries. He was thinking about something that was already used in medicine, considered safe, and was effective. He packed up some blue dye, syringes, and raced back to Hazard. He injected methylene blue into his patients, and within minutes their blue skin went away. So methylene blue is an electron donor. It gave an electron to all the 3+ irons, reducing them to 2+. The 2+ irons could now bind oxygen and change the color of their skin within minutes. He left them with the dye in an oral form to take every day to keep the methemoglobin and their blue skin in check. Let's talk about this color for a bit. Sometimes when I talk about hemoglobin, it sounds like I'm talking about the rainbow. And of course, physics pals and experts out there, feel free to add in and comment. When white light hits anything, and in this case, our body, some wavelengths are absorbed and some are reflected. And whatever is reflected is what we see color-wise. So let's focus on a blood vessel for now to talk about color. As a pathologist, I saw a lot of human tissue with vessels, and vessels aren't blue or red. They're normally tan pinkish with sometimes a very thin wall that could almost appear translucent. So here's our example from the front and from the side. Red light has a longer wavelength, which tends to get absorbed and scattered by the body. The wavelength of red light is between 620 and 750 nanometers. Blue light has shorter wavelengths with wavelengths of about 450 to 495 nanometers. Blue gets reflected by the body. So for this example, consider the blue reflection as our body's blue baseline, just like a touch of blue to this vein. And inside we have clear blood cells in here for now that will color in soon. When the irons in hemoglobin bind to oxygen, this binding doesn't absorb red light. Instead, it reflects red light. And it now absorbs infrared light, which is between 850 to 1,000 nanometers. 940 nanometers will be our number to remember for pulse oximetry later on. This reflected red light makes hemoglobin bright red, making the red blood cells red, making oxygenated blood bright red, and making the blood vessels pure red. Now, when iron is not bound to oxygen, the deoxygenated hemoglobin absorbs red light. 660 is important for the pulse oximeter coming up later. Methemoglobin also absorbs red light with a peak absorption of about 630 nanometers. If red light is getting absorbed, either with deoxygenated blood or methemoglobin, blue light is getting seen more. This is why veins can appear blue because of the deoxygenated blood within them, and this is why the blue people were blue. Methemoglobin that was coursing through their whole body was absorbing red light, which made them appear blue. The bluish discoloration is also called cyanosis, and also this is why their blood appeared brownish. It was absorbing red light. How did the blue people come to be? So first of all, they were missing that reductase because of a super rare mutated gene that both Martin and Elizabeth carried but didn't express. So it didn't show on them, they didn't have blue skin. To show blue skin by missing that reductase is an autosomal recessive disorder, so you need 2 copies of the mutated gene. Both Martin and Elizabeth carried 1 copy each, and to 4 of their children, they each passed down a copy, which led to those children having 2 copies, leading to their blue skin. Next, remember that 8-hour drive Dr. K-Wine took all the time? There were some roads back then, but there was no major highway that allowed for a quicker trip. Someone on TikTok told me that the route now is 2 hours. And even before the 1960s, like 1800s, there weren't any roads or railroads, which meant that the Fugits and the few families around Troublesome Creek didn't leave the area much, which led to a lot of them marrying one another, and so this super rare gene started getting expressed more commonly in a very small area. Methemoglobinemia is not just inherited, it could be acquired. So remember that to oxidize something is to remove an electron, something negative. So to oxidize 2+ iron is to turn it into 3+ iron. So some oxidants can cause an acquired methemoglobinemia. Anesthetics, particularly topical benzocaine, which can be used on a patient before having an upper endoscopy. Some antibiotics like dapsone and rifampin can cause it. Nitrites can also cause it, nitroglycerin or inhaled nitric oxide, which is laughing gas. Sometimes recreational drugs can also cause it. So at about 10% methemoglobin levels, blue skin starts forming. Above 20%, there can be more severe health problems affecting the heart and nervous system. Seizures, weakness, confusion, shortness of breath, and chest pain could be symptoms. Methemoglobin levels of 70% or more could be fatal. So usually seeing blue skin or cyanosis will lead to giving extra or supplemental oxygen plus running some tests. And there are some very interesting test results with methemoglobinemia. A lot of things don't make sense, which should raise your suspicion for a problem with hemoglobin like methemoglobinemia. If you check the arterial blood gases, you would find that the partial pressure of oxygen, meaning the amount of oxygen dissolved in the arterial blood, specifically in plasma, would be normal. Normal levels are 75 to 100. So it's a measure of how the oxygen from the alveoli in the lung has diffused into the blood, which is not affected by methemoglobinemia. It might possibly be even higher than normal, like higher than 100 if you're giving extra or supplemental oxygen. And seeing a normal partial pressure of oxygen in someone who is blue, it's interesting because it doesn't really make sense. And it's also interesting if you're giving supplemental oxygen, but the cyanosis isn't getting better. So these are all clues. Also from our ABG, we get the oxygen saturation. Now, this oxygen saturation measures how much or what percent of hemoglobin is binding oxygen. Normal amounts are 94 to 100%. The oxygen saturation might be normal in methemoglobinemia, but it's falsely normal since it could be calculated using that normal to high partial pressure of oxygen we just talked about. Lastly, pulse oximetry. It's another measure of oxygen saturation as well, minus the invasiveness of getting blood. It measures the absorbance of light at two different wavelengths, 660, which is red light that deoxygenated hemoglobin absorbs, and 940, which is infrared light that oxygenated hemoglobin absorbs. And that pulse oximeter calculates the oxygen saturation from measuring those two absorbances to give you a percent. Normal is 95% or higher, and it only measures those two wavelengths. So it won't measure methemoglobin, which absorbs at 630 nanometers. However, it will still give you an abnormal result, and it's usually about 85% or so on the pulse oximeter, which also doesn't make sense because a cyanotic person typically has an oxygen saturation level that's less than 80%, but the pulse oximeter will read out about 85. And not only that, if you compare this pulse oximeter reading to your falsely normal blood gas readings, they don't match up, which doesn't make sense. This is also called the oxygen saturation gap. So when you start getting these interesting results that don't make sense, make sure you think about methemoglobinemia.